So we're going to go over the Unit 7 practice test. In this video, we're going to look at the first 3 learning objectives. So the first learning objective is all about approximating areas with Riemann sums. So remember, Riemann sums are if you have some area that you're trying to approximate, you're going to use these kind of smaller rectangles to approximate the area. All right, so this first one, we're trying to approximate this area from 0 to 2 using left-hand sums and 4 subintervals. So whenever we're doing the Riemann sums, the first thing we have to figure out is how wide are our rectangles going to be. So here we're starting at 0 and going to 2, so that's a distance of 2. And we're breaking up into 4 subintervals, which is going to be 1/2. All right, so these subintervals are going to have a width of 1/2, which means the rectangles will also have a width of 1/2. So you can see for B, C, and D, that 1/2 is representing the width of all of these rectangles. And then we're just going to add together all their heights. All right, so what are the heights going to be? Think about our number line. We have 0 to 2. And we're doing distances or widths of 1/2. So the next thing we have is 0.5. Then we'd have 1, and then we'd have 1.5. All right, each one of these we're going to get a different rectangle. But how do we know how tall the rectangle is? We're using the left-hand sum. So the first interval, we're going to take 0 and plug it into the function I care about. So I'm going to do 0 squared, and that'll give me the height of my rectangle. The next interval, I'd plug in the left-hand side 0.5, and I would square it. The third interval, the left-hand side. The last interval, the left-hand side. So we can see we're plugging in 0, 0.5, 1, and 1.5. That is C. All right, so the 1/2 is the width of all of these rectangles, and then those are the 4 numbers that I'm plugging into my x squared function. All right, so here we have the function f of x equals x squared. Which of these would be an overestimate? So these are the types of questions the AP test likes to ask a lot is, we're doing a Riemann sum. Is that Riemann sum going to be more than the actual area or less than the actual area? All right, so I have x squared. Looks something like this. All right, we're going to do a couple different Riemann sums. So we're going to go from 0 to 2. Let's just say 2 is there, using left-hand sums. So if I do that, start at 0, I'd have the left-hand side, then I'd have the left-hand side, then the left-hand side. And look at that, I'm missing some pieces of the area I actually want. So this is an underestimate, not an overestimate. What if I do the same thing with right-hand sums? With right-hand sums, I would be drawing rectangles like this. And you can see those have extra area that I don't want in my answer, so that actually is an overestimate. So the right answer is going to end up being B. But let's just check the other ones to make sure. All right, -2 to 0 using right-hand sum. So now I'm using the right hand of these rectangles. And you can see there's some extra pieces in there that I'm missing. So this is an underestimate because I'm not getting everything. And midpoint sum, I'd do the middle of these rectangles. Would go through my graph. All right, this one's a little bit hard to tell, but the areas that I'm getting extra are smaller than the areas that I'm missing. So this one would also be an underestimate. So D is also out. So it just makes sense that B would be the right answer. All right, 3, we're going to use this table. And we're going to approximate 3 to 7 using right-hand sums. So they do this a lot where they give you a table and make you do a Riemann sum. We're going from 3 to 7. Okay, let's just think about our number line. We can see these have gaps 1, so they're gaps of 1. And each one we're going to use the left-hand value. So our first interval we're going to use 3, our second interval we're going to use 4, third interval 5, fourth interval 6. And the nice thing is these are with 1, so we're basically just going to add all these heights together. So when I plug in 3, 4, 5, and 6, when I add those together, I get 9. Right, so the answer is 9 because these are the left-hand sides of each of these intervals. And the width is just 1, so I don't have to multiply them by anything. And for our short answer, we want to approximate this integral using 4 subintervals and a midpoint approximation. So again, first thing, how wide are our intervals? We're covering a distance of 8, and we're breaking up into 4 equal pieces, so our intervals are width 2. All right, so we're going to look like this on the number line. We're starting at 0, 2, 4, 6, 8. But for each of these intervals, we're using the midpoint. So the middle of 0 and 2 is 1. Middle there is 3, 5, and 7. Now we're going to get the heights of all these rectangles by plugging this into our expression. So 2x plus 1, 2 times 1 plus 1 is 3. 2 times 3 plus 1 is 7. 2 times 5 plus 1 is 11. And 2 plus 7 plus 1 is 15. All right, so those are the heights. All right, this one, the widths are 2, and the heights are given here. So now each individual rectangle, I multiply these by 2. 6, 14, 22, 30. All right, so these are the areas of each individual rectangle. And then I just add them all together to get 72 as my final answer. All right, so just taking these rectangles, all right, the height, and each of those times the width gives me what's in green. All right, our next learning objective is still about Riemann sums, but it's connection to summation notation and their connection to definite integrals. All right, so which of the following definite integrals is equal to this whole thing? So if you see a limit as n goes to infinity of something like this, this is basically what's happening when you take your rectangles and you make them super small. All right, so we have all these really, really small rectangles, and that's going to give me the exact area. So this part, the limit as n goes to infinity, basically doing an infinite number of rectangles, that's the same as our integral symbol. And then the way I like to think about these ones is k is a thing that changes in my summation notation. So the first thing I do is plug in k equals 1, then I plug in k equals 2, k equals 3, and so on. So k is the thing that's changing. All right, so k is going to kind of take the place of x. So everywhere you see a k, there's probably going to be an x in your actual expression. All right, the other thing is the piece that doesn't have a k in it, that tells you the width of your rectangle. So here we're taking a distance of 5 and breaking it up into n equal pieces. So it tells me the distance I'm covering has a length 5. All right, the A goes from 1 to 6, that's 5. B, 1 to 6, that's 5. C, 0 to 5. All right, so all these have a distance of 5, so that really doesn't help us too much. But the 5 over n part represents how far you're going along each step in your rectangle. So if we take that and multiply it by k, that's pretty much where we're at for our next rectangle. So 5k over n, this represents the x value that we're talking about. And then this one, 10k over n isn't exactly 5k over n, but 10 is 2 times 5. So 10k over n is 2 times 5k over n. And the 5 over n talks about how many steps 5 over n is the interval length, k is how many steps you've gone. That's going to kind of be the replacement for your x. So we're going to have the 2 and the x, 1 and an x, and then this is just the width, so that goes away. So our answer ends up being D. All right, so the hints for these ones, all right, the thing that's changing k kind of corresponds to our x's, so we have these two x's. That's how I know C is not right and A is not right, because there's two different k's in there. And then the width of your rectangle times k is kind of your placeholder for your x. All right, so we can use these same tips to answer number 6. Which of the following definite integrals are equal to this sum? And I just realized there's a typo. This should look like the integral from -1 to 4. All right, so which one of these are equal to this thing? All right, the first thing is for this 5 over n part, makes it look like our width is 5. All right, so -1 to 4 is 5, 0 to 5 is 5, so those look right. 0 to 1 does not look right now because that's only a distance of 1. All right, the place that has a k is going to be kind of a placeholder for x. All right, so this first one, if I have -1 plus x in the parentheses with sign, that looks like that one should be right. So this one does look like it's going to be right. But we can kind of shift everything to the left and start at -1 instead. So our values that we're plugging into our sums start at -1, and then we have to add stuff to that afterwards. So if we start at -1, then all this stuff makes sense. And then this whole thing represents the x. Actually, we got that -1 where we're starting. All right, and that makes this one true. Because if I start at -1 instead of 0, then this -1 has to be there the whole time. And if you look at our options, the only possible answer now that we know 1 and 2 are right is D. All right, but why is the third one right? The third one's right because what I could do is take this 5 and I could factor it out of everything. So there's just a 5 out the front, and that changes this to 1 over n, which means my distance is just 1, like 0 to 1. And since there's 1 over n, turns into k over n represents x, the k over n part's x, and I have that extra 5 in front of x. So changing things around and moving numbers around is how 3 also ends up being right. But again, looking for that k is kind of your hint, that's the x, and then this is your hint for the width of your rectangles. And here we're just doing the same things, but in reverse. So we want to go from 2 to 8 of cosine of x squared. The first thing is 2 to 8 is a difference of 6. So we're going to take 6 and break it up into our rectangles. So automatically, I know a is probably not right because that's 1 over n instead of 6 over n. All right, the next thing I know is I'm going to take cosine. And what is the x going to be represented by? All right, well, I'm starting at 2, so I'm going to start at 2. And I'm going to add the width of my rectangles, and then how far I've gone to the right, which is the k part. Right. So that is going to represent my x. It's where I started, plus how many times I've gone to the right, and that is going to be squared with cosine. All right, so which one looks like that? That looks like D. And the last one is just making sure you understand what this summation notation means. Remember, it just means you're adding together a bunch of things. You start with 1, so you plug in 1, you get 1 squared. And then you just increase each time. So I'm going to plug in 2, plug in 3, plug in 4, plug in 5. All right, once I get to the number on the top, I stop. So I don't want to do this, all right, because I stop at 5. All right, so that's going to be 1 plus 4 plus 9 plus 16 plus 25. All right, and just to add those real quickly together with the calculator, and I get 55. All right, so this one, again, just double checking to make sure you know what this actual summation notation means when it's not being made more complicated with all this Riemann sum stuff. All right, and the last objective we'll cover in this video is the fundamental theorem of an accumulation functions. So for us, this was the fundamental theorem, part 1, which has to do when you start mixing derivatives and these integral symbols. All right, so you can read through this first problem. All right, so it says, which of the following defines a function that measures the accumulation of water? So accumulation is going to end up turning into an integral sign in the pool from 1 to x. Well, only two of these have an integral symbol, so B and A are out. It should be 1 to x or 0 to x. Well, we're starting at 1 and we're going to x, so the answer just has to be D. All right, an accumulation from 1 to x of whatever function we're talking about. All right, the next one is we have our f already defined as an accumulation function, and we're going to take its derivative. And the fundamental theorem of calculus, part 1, says if I do this, all I basically have to do is take this and plug it in for the t's. All right, so there's nothing else you have to do, so I should get sine of x squared plus 5x. All right, so when it's just a number down here and just an x, you just put the x, you basically just write x instead of t. All right, 11 is going to be a little bit more difficult. We still start with a number on the bottom, but now up top we have cosine of x. So still going to do the same first step and just take that top and put it in for t. All right, so instead of t squared, I get cosine of x squared. But this is a chain rule problem because that cosine of x is inside of that bigger function. So I also have to multiply that by its derivative, which is negative sine of x. All right, so this negative sign, I could just take and write it at the front and see that D is the right answer. And lastly, the short answer for this, we want to calculate the derivative. This one, more complicated because I have an x and an x squared. All right, I don't have a number at the bottom like we had in the previous steps. So the first thing is, remember, I have to start at a number. The easiest number started as 0. All right, so I'm going to start at 0. At some point, I'm going to hit x, which is on the bottom, and then another point, I'm going to hit x squared. Right. If I have to start at 0, I can go from 0 to x squared, or I could go from 0 to x. All right. And if you kind of cancel out those two pieces, the leftover part is what I actually want, which is x to x squared. All right, so I'm going to do the 0 to x squared part. I'm going to subtract the 0 to x part. And nothing else changes. I basically just split this one thing up into two separate things, but they're equal based on that little picture I drew. Now I do the fundamental theorem. All right, for this one, because it's an x squared up here, I have to do the chain rule. So the x squared is going to go in first. I'm going to get x squared squared. Then I have to multiply that by its derivative, which is 2x. All right. And then the second one, I just have an x, so I just put the x in and I get x squared. And so of course, I don't really make you simplify too much, but if you wanted to, you could write this as 2x to the 5th minus x squared would be your final answer. All right, so that's the first 3 learning objectives on our Unit 7 test. And now we'll go on to the next 2 in the next video.